Hello, good morning, good evening, good afternoon, everybody, wherever you might be. Hola, buenos dias, buenas tardes. It is my great pleasure to introduce a speaker from Malaga, from Spain. So it's, I think, first time ever that we have a speaker from Spain. So I think after over 25 years of running this seminar, it's for the first time we have a speaker from Spain. Unfortunately, only via Zoom, not in person, but maybe another time. So our speaker is IVÁN RUIZ Campos from Spain, from Malaga, and he will tell us everything and more about the associative commutative representations of evolution algebras in dimension 2. It's all yours. Take it away.
Okay, thank you so much. Thank you so much, first of all, for the invitation. It's a pleasure for me to be part of this seminar. I hope I'm up to the level, since I'm still considered a student. So, well, this was a work that we did with my colleagues. This was done with Yolanda Cabrera, Daniel Gonçalves, which I think you might know, María Inés Gonçalves, Dolores Martín, and Cándido Martín. Cándido Martín is my supervisor in the thesis. This is not part of my thesis, so I wouldn't consider myself an expert, but I will do my best. Okay. So as I mentioned, we're going to talk about representation of evolution algebras in dimension 2. So first of all, we see a little bit about evolution algebras, brief motivation, things like that. And after that, I'm going to talk about like the keys of the paper that actually I'm going to talk a little bit. And we're going to see about affine group schemes and Hopf algebras, affine group scheme of automorphisms of an evolution algebra. Later, we'll go to associative representation of evolution algebras. And later, we'll go to what the paper says, or the main result of the paper, which are representations of Hopf algebras and how they relate. Okay, so if there's no doubt, let's see a brief motivation, a very small one. So if we consider an associative commutative unitary algebra U given by this quotient over here, with K is a field, we have the polynomial rings with two variables, and this ideal over here, we can consider an involution induced by just the conjugate given by the square, in like x bar goes to y bar square, and y bar goes to x squared, where bar denotes the classes here in the quotient. Okay, so we already have an associative product here, but we can consider a new product P given just using the involution here. And if we define A, the vector space generated by x bar and y bar, then we can observe the following. And if we make the product of x times x, we obtain y. If we make the product of y times y, we obtain x. And if we multiply x times y, we obtain 0. Okay. And what is this? So we have that AP is an algebra, and it's also an evolution algebra contained in U, which is a very different algebra from the original. Okay. But what we have to do is changing the product. Okay.
Sorry, just a stupid question. When I say unitary algebra, you simply mean unital algebra.
Unital, yeah, sorry. Sometimes I make that mistake a lot. Yeah, unital algebra. Yes, with a
because you also have the star and involution, so one is tempted to think about the unitary elements.
sorry, my bad.
No worries.
Okay, so something similar happens in Lie algebras. Maybe you will find it more common. So if we have a Lie algebra, then that algebra is a subalgebra of its universal enveloping, associative universal envelope, but just changing the product by itself. Okay, so what we obtain is we gain an associative algebra that contains the previous one, but we have to twist the product. Okay, and this is something similar, or something that we will call later a representation. Okay, and in this case, this representation is faithful. In addition, the universal envelope of the Lie algebra It's a Hopf algebra relative to this following coalgebra operations, given the coproduct, the coinverse, and the augmentation, given in this way. So we can see that there is kind of a relation, at least in this motivation, between Hopf algebras, representation of an algebra, ways to introduce the algebra in an associative one by twisting the product. So that's what we'll do here, okay? So this talk is related to a work that first studied my supervisor and their colleagues in a paper called Square and Associative Representation of Two-Dimensional Evolution Algebras, where also Mercedes Siles participated in, where they studied automorphisms and representations of evolution algebras of dimension 2. And they observed there that there might be a correlation between automorphisms and representation of an evolution algebra, which we confirmed later in the paper called Hopf algebras and associative representation of two evolutional algebras. Okay, you can find that paper there, but also with Yolanda Cabrera and, well, myself. Okay, good. I've mentioned several times evolution algebras, so let's see what it is. So they were introduced by Tian, and also I'm not sure if I'm pronouncing this correctly, Wojciechowski, maybe, if I'm wrong, correct me. And they introduced it in the mathematical concept of evolution algebra in Mendelian genetics, where they try to model asexual reproduction using algebra. Okay.
So my joke wasn't all that stupid. It is related to genetics.
Yeah, it is. They were, but not by Darwin.
Yeah, of course.
yeah. Okay. So the definition is quite easy. It's very basic. So if you have a K-algebra, it is an evolution algebra. If there exists a basis V of elements of as a vector space, such as the product of two different elements, it's 0. And in this case, we call that basis natural basis. Okay.
Why not orthogonal?
Sorry?
Why not orthogonal basis? I mean, if you would do it for a Hilbert space, you would say it's an orthogonal basis.
I would think just because, well, first of all, Tian is not an algebraist, so maybe that's why they didn't choose that name. Also because you don't work with a metric or something where you have orthogonality in that sense. But you can say, I would also say orthogonal, but in the similar way as a orthogonal set of idempotents, but they just call it natural because here these elements are like the different genes in a species. So it's like there are natural genes, something kind of like that. I don't know.
Yeah, and also, you know, multiplication is not exactly a scalar product. So yeah, would be an abuse a little bit anyway. But maybe when I see EI, EJ equal to 0 for different IJ, it looks to me like orthogonal, but okay, let's keep it.
Yeah, maybe it is related to natural selection.
Yes, of
Darwinian
course.
after all.
Natural selection, that's why natural base. Yeah, good point, Adam. Good point. Thank you.
Okay, thank you. So this kind of algebras, usually they are not associative. For example, if you consider an algebra that verifies that EI squared equals EJ and EJ squared is different from 0, then this product equal EJ squared, which is different from 0. However, this other product over here, which if it was associative, it will be the same. It's 0 because EI times EJ equals 0, so the rest of it is 0. So generally it's not associative, but we will see examples of evolution algebras that are associative. But it always verifies that it's commutative, which is, for me, it's quite impressive because always when I think of a commutative algebra, I always think of it as an associative algebra. Yeah, but this is a good example of something that it's not. And it's quite easy. It's a quite easy definition. So once you know how this natural basis, you can define the product just by knowing the square of these elements, where EI squared equals a finite sum of a linear combination of vector spaces in this basis. And this will be the scalars, the omega ik. Okay.
Wait, so
And
do
if
you
you-
assume that lambda is finite or not
No, you
necessarily?
don't have. It doesn't
Okay.
have to. But there's a finite. There's a finite number of elements.
Okay, yeah,
different from
finite
zero.
non-zero, of course, yes.
Yeah, but in this talk, I will be talking about dimension 2. So lambda is very finite.
Yes, 2 is a very finite number.
Okay, so once we know the product, once we know that we have a natural basis, we can define what is called the structural matrix of the evolution algebra, which is just considering all the structure constant, and observe that usually you have a tensor of in an algebra you would have a 3-dimensional tensor, whereas in evolution algebra, since you have lots of different elements that are 0 because they are orthogonal or natural, you get a matrix, a square matrix. And just there are many other definitions that I would like to say, but we will just say that an evolution algebra is perfect when the square of the algebra equals the algebra, which is equivalent in the finite dimensional case to the determinant of the matrix being different from 0, all the matrix being regular. That's so if sometimes you might find some papers where instead of using perfect, they refer this kind of algebra as regular. Okay, in infinite dimensional case, this is not true. Okay, always refer as this. Good. So we know what an evolution algebra is when an algebra is perfect. So let's see what a graph of an evolutional algebra is. So graphs of evolution algebras were introduced by Alberto El Duque and Alicia Labra in a paper called Evolution Algebra and Graphs. So how do we associate a directed graph to evolution algebra? So given an evolution algebra with natural basis given by V, we can construct the associated directed graph EA by just consisting of a vertex for each element in the natural basis and an arrow for each element different from 0 in the structure matrix, where this arrow goes from the vertex Vi to the vertex Vj if the structure constant omega ij is different from 0. Let's see an example which I think would might find things easier. So if we have A and R evolution algebra of dimension 2 given by this basis E1 and E2, such that product is given by here, this operation, the graph that models this would be this one over here. Observe that since all the structure constants are different from 0, we have an arrow that connects with every vertex. Okay, but here the information, there's a little bit of lack of information. So usually we represent the direct graph of an evolution algebra using weighted graphs in this way, where instead
do you realize that this is the graph of the famous Kunz algebra O2?
Sorry?
Do you realize that this is a very famous graph, or actually it's a graph of a very famous C-star algebra O2, Kunz's O2. This is Kunz's O2.
I'm not very familiar with C-star algebras. I just know a little bit of Steinberg algebras and Levith-Path algebras, but I didn't know that, which is good that I chose this kind of graph.
Yeah, that's a very interesting graph. It's the line graph of the original Hawaiian earring graph.
Oh,
but
okay.
This gives you an isomorphic algebra. And in fact, this is a Levit algebra because Kunz algebras, when you take just the dense part, the polynomial subalgebra, then they are exactly Levit algebras of type 1, n. So this is a Levit algebra of type 1, 2.
Okay, good. Nice. Quite interesting. Thank you.
Yes, Ali, you have a question?
Yes. I'm sorry, I lose the point. What is VI and Fij in the definition? Maybe I lose the point and the definition. What is VI and Fij?
VI is VI is in the basis. Wait, this is also confusing. VI is in the basis? Oh no, this is just a name. It's like, a name.
Yeah, it's like, I mean, because this space is different from this one. So you consider graphs in one category and the element and vector space in the evolution algebra. This is just part of a definition, but you can consider just the name as this way. Maybe this made you more confused. I was just trying to be more precise. But
No,
you just
it's just relabeling, but this is being precise. Rigorously speaking, one should do what IVÁN did. It's a different set. But basically, you see that vertices are basis elements and edges are these non-zero scalars.
Yeah.
So VI are the base of the algebra, yes? VI are the base of algebra?
No, they are just elements from a different set. It's just vertices. But you can, even if you want, you can call these vertices EI, just as the exactly. But it's not, it's not so, I would consider, I don't know how to say that, like...
Yeah, there's a certain abuse. One is an element of an algebra, an element of a graph. These are apples and oranges. So he's just being pedantic, okay?
Yeah.
Yes. Okay.
Thank you.
Sorry, IVÁN,
actually on
the view. Yes, Ludwig.
On the drawing, I think they called E1, E2, these vertices.
Exactly. So which added the confusion, yes.
Okay. Any more questions?
I don't see any raised hands, so go ahead.
So usually what we do is we represent it in this way. So we make an abusive notation and we call the vertices in the same way as the elements in the natural basis, and instead of using the arrows, we just use the weights that they have, the structure constants.
And by the way, I hope you guys noticed that you moved from evolution to revolution. Right? This is a revolution algebra.
Okay. So let's continue. Some things that I like to highlight in this case of evolution algebras is that the associated graph depends on the chosen basis. Because, for example, if you have if you have an evolution algebra, you can find two different natural bases, and the directed graphs that model that algebra is completely different. They are not even isomorphic. And sometimes there are some properties that you cannot deduce from the graph, at least by the ones without the weights. For example, perfect or not perfect, like you can have two graphs that model two different evolution algebras that are not isomorphic, and the graph is the same. Okay. Well, as I mentioned, different evolution algebras can have the same graph. For example, the evolution algebra with the structure matrix given by 1, 1, 1, 1. This one is not perfect, whereas the other one was. And the graph is the same, like the directed graph without the weights and without like just the one that models, like the graph without any more information.
By the way, let me ask you a stupid question.
Okay.
If instead of just a directed graph, you would take a labeled directed graph, okay, very much used as well, then the algebra, the evolution algebra, wouldn't be uniquely determined?
In that way it is. Yeah.
Okay.
You think, but like, but if you change the basis, you can.
That's okay. That's okay. We have the same in graph sister algebras. For instance, I already told you that this beautiful candy-like graph gives you the same sister algebra as the Hawaiian earring graph. So we have the same sister algebra when we take the graph like this, just two loops. Okay. Then this graph and that graph give you the same graph sister algebra. So non-uniqueness is, we are used to it. But once you have a graph, you uniquely determine its graph sister algebra. So that was a little bit of a bummer for me. This is why I asked my question.
Okay, let's see. So yeah, I'm going to focus on evolution algebra of dimension 2. So it's quite easy. And they were, as I already mentioned, they were studied in this paper, Squares and Associative Representation of Two-Dimensional Evolution Algebra. And in that paper, they also give a full classification of all the families of isomorphism classes of evolution algebras of dimension 2, which are these ones over here. they are called, this family of algebras are called A0, A1, A2 alpha, A3 alpha, A4 alpha, A5 alpha beta, A5, A6, A7, A8 alpha. If I'm not wrong, this, well, not this one, but this over here are perfect, and this one are non-perfect. So let's see more in detail what are these families. So the first one is the trivial algebra, which is an evolution algebra. You multiply anything by anything, it gives you 0. It's not a very interesting algebra by itself. And following the perfect dimensional case or the regular case, we have A1, which can be represented by this graph. You obtain E1 squared equals E1, E2 squared equals E2. This one is perfect. You obtain this also A2 alpha, this family, depending on the parameter alpha. We can obtain A3 alpha, which is this one over here. Again, depending on a parameter alpha. These three over here, as I mentioned, are perfect. Also, there is this other one, A4 alpha and A5 alpha beta, which is the one that gives you the Hawaiian ring in the C-star algebra. And in this case, alpha and beta has to verify that the product of them is different from 0 and from 1, okay? In the non-perfect evolution case, we have the A5. Observe that here, this is these are linear dependent, the product, so it's not perfect. Here you have a sink and a source, sorry, a sink and a source, so it's again not perfect. A7 is also non-perfect because you have here an isolated vertex. And lastly, you have A alpha, which is this one over here. So what I'm going to talk in this talk, valga la redundancia, as we say in Spanish. So we want to check if there is a connection between automorphisms of an evolution algebra of dimension 2 and their faithful associative commutative unitary representations. How we will do that? So we will compute the automorphisms of an algebra A for all the families of evolution algebra of dimension 2, and we will study their corresponding affine group scheme that I will define later. And after that, we will check if they have a faithful associative commutative representation. So this paper or this work it has a lot of brute force. We did lots of computations. We even use a few softwares. So it's quite a tough paper to read, at least for myself. So,
by the way, these evolution algebras, I'm sorry, but I'm trying to remember it. Can you go back to the definition of evolution algebra? Just I want to make sure I'm with you. Okay, you say either exists a basis, but do you assume associativity? No, it's not associative. That's the point.
No, it's not.
Okay.
It's not associative.
Okay, thank you.
Is it a Jordan or Jordan algebra? Is it power associative or things like that?
Oh, good.
Alternative?
No.
Do you have some properties?
No, the thing is, for example, Jordan algebras, Lie algebra, this kind of algebras, they are defined by not a property. What's the name? By an equality. So the elements of the algebra are in a variety, in a regular, in a surface kind of thing. So, which is something that doesn't happen in evolution algebra, which is quite weird and quite strange.
Okay.
For example, something that happens in Jordan algebra or Lie algebras or associative algebra or alternative algebra is that a subalgebra of itself is also the same type of algebra. It remains in the category. However, in evolution algebra, that doesn't happen. If you have an algebra, an evolution algebra, and you have a subalgebra of it, it doesn't have it's not necessarily an evolution algebra because you don't have an equality that all the elements verified. But right now, like a couple of weeks ago, a colleague proved they made a paper where they proved that subalgebras of regular evolution algebras, they're still regular. So there's this improved the concept in a similar way to Jordan algebra. Okay, so where was yeah,
But could you go back to these examples for a second?
sure. These
Even,
are all the families.
even further, the previous one. No, there's a page which we just were on recently and now it's gone. Yeah, this one. So sorry if you don't mind me being again obnoxious. We very much know these graphs because, for instance, the bottom graph is the graph of the very famous quantum group SUQ2. That's the graph of quantum SU2 sister algebra. This is just matrices, 2x2 matrices over the circle. And this is just two circles. But this graph is very important for us. This is a quantum 3-sphere.
Oh, wow. Nice.
I know it's irrelevant, but I couldn't resist the temptation.
No,
Tomek,
no, it's not irrelevant. I'm glad to if that stuff like this kind of examples also appear in other areas. So I really like it.
Tomek, you have a question. Go ahead.
Yes, I have a question. My question is about the definition of this evolution algebra. So if I understand well, you are starting from a magma.
From a what? Beg your
and
pardon?
you are introducing
magma.
You are introducing relations. It's a binary operation. Because when you are writing identities or you are talking about an ideal, not first defining in which algebraic structure you are allowed this congruence, it doesn't make sense. So you first you have to define the class of algebras in which you are considering your relations.
Okay.
So my understanding of your definition is that you start from a binary operation, arbitrary binary operation, which is called magma.
Yeah. Yeah.
Okay. Okay. So it's a quotient magma.
I don't know because I don't know about magmas. I just I know that in an evolution algebra, it's an algebra. Like you have a product and a binary operation.
Yeah,
it's compatible.
So if you have a binary operation, it's called magma.
And the thing is that there is a basis of this algebra as a vector space that verifies that the product of them is 0 for all of them.
Yeah,
that's all. And there are few examples, like, for example, if you consider, I don't know, with K being a field, K squared with the product by component wise, that's an evolution algebra, for example. Which in this case is also associative, but generally it's not. That's, I don't know.
I'm asking because you explained the difference between this kind of definition and the definition of an algebra as a variety. It's not defined by identities.
No, what I said is like this algebra is not a variety. Something similar, like for example,
this algebra doesn't belong to an algebra to a variety of algebras.
Okay.
Okay. It's a quotient magma with respect to some generators and some relations.
Okay.
Good. Thank you.
Can I ask also, so you classify them by giving the square of E1, E2. Why you on the right-hand side, E1 square cannot be, I know, E2 to the third power? They are linear only on the right-hand side always.
Because if you have the squares, you can make any other product.
Yeah, that's true because of this orthogonality or naturality.
Yeah, you can obtain any other power just by that one.
Okay.
Because
okay, so they are represent up to isomorphism. Okay.
Yeah.
Okay, thanks.
Okay. Where I was. Okay. Yeah, affine group schemes. One of them, the reference that I use for affine group schemes, I'm not an expert at all. I don't know anything, but I really like this book about called Introduction to Affine Group Schemes by Waterhouse. And basically, an affine group scheme, or the way that he defines it is a functor from the category of associative, commutative, unital K algebras. In this case, I'm going to use K as a field, a functor from this category to groups such that U here is the forget functor. Like I forget about the structure of groups and I consider that this is just sets. In this case, this functor is representable. That's an affine group scheme. And in particular, it means that there is an algebra from this category that for every other element, we have that FR is in bijection. The element of this group are in bijection with the homomorphisms from the, I changed here. Sorry, this is a typo because I didn't change this one. I changed most of them. This should be H, or in this case, IA, okay? The representing algebra, from the representing algebra to R. Okay.
May I comment on
Sure.
your definition? Of course, it's a very abstract definition, but it boils down to saying that H is a commutative of algebra.
Yeah, that will appear later.
Okay. Sorry.
That will appear. Okay.
But why Hopf? Sorry, I understand, Tomek. Where is the Hopf structure coming from?
Because it's a
From
functor to group.
From the group's property.
Oh, yes, of course.
And the Joneda's lemma. I will talk about
yeah.
that in a couple of minutes. Okay. So also, if you have an affine group scheme F, such as the FR is a collection of tuples, like there is an algebraic variety of them, they form an algebraic variety, then you can obtain the representing algebra just by considering the quotient of selecting as many variables as you have in each element, and an ideal form by the polynomials that they verify. Okay, so that's the way that we will find the whole algebra of our affine group schemes that are related to the evolution algebras. Some examples, so we have mu n with representing algebra given by the group algebra of the cyclic group, sorry. GL, which is general linear matrix ring, and this representing group representing of algebra, also the multiplicative one, where the elements are the unit elements in the ring, and the representing algebra is the Taylor polynomials. Okay, so once we have an affine group scheme, we can obtain a Hopf algebra, as you might already know. So since we know that FR is a group, we have a product, we have an inverse, and we have an identity. So for each element in this category, we have a product, an inverse, and a certain element identity. Okay, and it can be proven, which is quite easy, that M, S, and I are natural maps. So we can use Joneda's lemma, which says that if we have two representable functors represented by A and B, having a natural bijection between a natural morphism between these two categories actually comes from a morphism from the representing algebra B to representing algebra A. Observe that there is an inverse of the sense of the arrows. These go from F to G, whereas the morphisms go from B to A. And how do we use that? So since we have a family of, since we have three natural bijections, natural morphisms, we can obtain delta S and epsilon, also known as the co-multiplication, co-inverse, and augmentation, given that A, in this case, is the representing algebra of the affine group scheme F. And also, since they verify certain properties, for example, you have that the product is associative, the inverse of the inverse gives you the same element, etc., etc. You have that these morphisms over here, using the Joneda lemma, verifies these three properties. In particular, that you have that I is a Hopf algebra, also a commutative Hopf algebra. Okay. So how are we going to assign an affine group scheme to an evolution algebra? So if we have R, an associative commutative unital K algebra, and A is an evolution K algebra with natural basis, given by this set. We can extend the scalars of the algebra, which is just isomorphic to consider the scalars in the ring in R, and use the module and the product, etc., in the similar way as in the evolution algebra. And you can define the representable functor, at least for the finite case, in this way. You fix a ring R, well, an algebra R, and you consider the automorphisms of the extended scalar of the evolution algebra. In the case for the morphisms, if you have a morphism from R to S, then you obtain a morphism from the automorphisms of AR to automorphisms of AS. In this way, if you have an automorphism of AR, then you obtain that it's the one that sends A times 1S to the one given by this formula over here. But we won't be very focused on this. Since we're working in finite dimensional case, we will be just using this to compute all the necessary. Okay, so we will use different tools to find different affine group schemes. One of them is given in Evolution Algebras Automorphisms of Graphs, again by Alberto El Duque and Alicia Labra, where they prove that if A is a perfect finite dimensional evolution algebra, then this sequence of affine group schemes, this is the diagonal group of the graph of associated to the evolution algebra, and this is the automorphisms of the graph of the evolution algebra. This sequence is exact. However, in the families that we are using, some of them are perfect, but some of them are not. For example, we can use this for A1, A3 alpha, A4 alpha, A5 alpha beta, but not for all of that. For the not perfect case, we will use classical computation. Okay, so let's jump to an example.
May I have a question?
Sure.
Yeah. In the middle, you have this
boldface.
Okay. Have you defined this object?
Yeah, here. This is the.
So this is this.
Yeah.
Okay, and out R is okay. I understand. Thank you. So can you come back to this picture, to this next slide? Yes. So it's not known if this rho is surjective.
No, it is not known, and actually, I think in some example, it's not.
It's not. In general, it's
not. But in some of them, it is.
Okay. So my next question is about this sequence. In what category you are considering your sequence? Because in the middle you have a scheme.
Yeah.
The counter domain of rho is a set theoretical group. In a sense, it's a discrete group.
This one.
Yes.
Yeah. It's all of this is as an exact sequence in the category of affine group schemes. This is the affine group scheme of a fixed group.
Yeah, but so you allow schemes of not finite type, or are you assuming that this automorphism group is finite? The counter domain of rho.
For the finite graphs, it is.
No. I'm talking about automorphisms. Because the problem is that if you have a finite set, you can give to this set a structure of a scheme. But if you have infinites, then you can say that you have infinite number of components. Or it's a difficult problem of finding an appropriate category of schemes in which you can speak about infinite sets. So probably there's a standing assumption that everything is finite, and then it can be given a structure of a discrete scheme, which is finite because it's algebraic.
Okay, I think in this paper everything is finite.
Okay,
That's why
if finite,
they cannot.
then it's okay. Okay. Now I understand. Thank you.
Okay, you're welcome. Thank you. So yeah, in the non-perfect case, we will have to use classical computation, and I will do an example with the whiteboard. Let's see an example of how to compute the affine group scheme of an evolution algebra. So if we have an evolution algebra of dimension 2, and we have an automorphism here, you can get the automorphisms by knowing the image of the vector spaces. In this case, we consider that f of E1 goes to A E1 plus V E2, and F E2 goes to C E1 plus D E2 with all these elements in the ring. Then for this map to be an automorphism, it has to verify this family of equations. You have to get that f from the product of E1, E2 equals the product if E1 to F E2, which goes to 0. We also have to verify this one, and also since it is an automorphism, this element has to be a unit of the ring. Okay,
I'm a bit confused. So why you are talking over a ring, not a field? And then what do you
not
mean by
a ring? Sorry, R is it's an element in the category of commutative, associative, unital K algebras, which can be a ring, for example.
Can I explain? Can I explain?
Yeah, please do, Tomek. Yes.
The point is that, in fact, this algebra was defined as an algebra representing some functor. So in a second, you will see that these coefficients A, B, C, and D will become variables.
Like it's like families,
to obtain the Hopf algebra.
Yeah. So we are looking for a universal Hopf algebra coacting on this evolution algebra, in a sense, preserving the structure. And this is the universal coaction, which means that you have to regard this A, B, C, and D now as variables, maybe satisfying some identities. Okay. For this, you need a functor, full functor. You cannot assume that you have automorphisms of some algebra over a fixed field.
Yeah. Thank you.
Okay. So, for example, if we consider the algebra A6, this evolution algebra, which is A1 squared equals 0, A2 squared equals E1, then an automorphism F that goes to the scalar station of AR, given by these 4 variables, has to verify these 4 equations over here. This one comes from this one, the second from the second, the third from the third, and obviously the last one comes from these 3 and this one over here. So these equations translate into these elements are of the form of this. You can write them as matrices of this form, where C is an element in the algebra R, and D is a unit in the algebra R, with the group operation given by the product of matrices in here, and also you obtain the inverse in this way. So you can see the elements of the automorphisms as tuples of the form X, Y, Z in R3, such that Z is the inverse of Y. Like, as you can see, you have like these matrices. Actually, the elements that give you information are C and D, and you know that C is any element in the algebra and D is an inverse. So how do you say that D is an inverse? By saying that you have the inverse of this element. You have in that YZ equals 1, with a product given by this one, which is just using this over here and changing the X and Y. So they are variables. So from this previous example, and using Joneda's lemma and all the things that we have to know, the algebra, the Hopf algebra that represents this affine group scheme is the one given by this co-multiplication, this co-inverse, and this omission over here. Okay. In some cases, the characteristic of the field, you have to be quite considerate with that because it will affect the affine group scheme. For example, in A5, in the automorphism of A5R, you obtain this family of automorphisms. However, when the characteristic equals 2, this affine group scheme equal the affine group scheme given by the multiplications, and this affine group scheme has this representing Hopf algebra. Whereas when the characteristic of the field is 2, you obtain the adding group scheme with a completely different Hopf algebraic structure. I will go back again so you can see the difference. And also see the Hopf algebra by itself as an algebra changes. You have here the Taylor polynomials, and here the polynomials in one variable. Okay, so I think I have done that quite fast, and it might be easier if I check on the paper, and also it will allow us to take a moment to breathe, also for myself. So if you give me a second, and I can share my screen.
You are at what altitude?
Sorry?
At what altitude are you?
Well, I'm at sea level because Málaga is in the south of Spain, but I'm in a 6th floor, so I don't know.
Yeah, so that's
20 minutes or something. But an hour and a half of talking is quite challenging for myself. So I would really appreciate these 30 seconds of just changing the screen.
By the way, you still have 43 minutes for your talk.
Yeah, I know. I still have plenty of things to tell. So, yeah. No, you cannot see. Why cannot I share my screen? Okay. Now, good. So let's see another example, another way of computing this. Well, not another way, the same way, but with more detail. So we will consider the algebra A1, which is given by A1 squared equals A1, A2 squared equals A2, E2. Okay. Good. So we want an element from automorphisms of A1R with R an element in LJK. Okay, so we can consider that FE1 is A1 plus BE2, FE2 equals, sorry, CE1 plus DE2. And we want this to be an automorphism, so it has to verify the following. So FE1 times FE2 has to be FE1, E2. And since this is an evolution algebra, this product is 0, which means that this is F of 0, which is 0. We also have, so this translates into AE1 plus BE2 CE1 plus DE2. This is equal to ACE1 plus BDE2, which is equal to 0, which gives us AC equals 0 and BD equals 0. Okay. We also have that FE squared equals if E1 squared. So we have that F A F E1, which I remember that's the square of A1. This is equal to FE1, which translates into AE1 plus VE2 equals to A square E1 plus B square 2, which means that A square equals A, B square equals B. And analogously, we obtain that E square equals FA2 square, which is FA2, which is CE1 plus DE2. And this is equal to C square E1 plus D square E2, which means that C square equals C, D square equals D. And also, since F is invertible, we have that A, D minus CB belongs to the units, which means that there is some element in R such that AD minus CB times U equals 1. And we have also this one, B, C, C, and A, C equals B, D equals 0. So if we use all of this, we can obtain the following. Okay, so if we multiply this equation by A, by D, by C, and by B, we can obtain the following. We can obtain that AD U equals A. We can also obtain that ADU equals D. This is by multiplying by A. This is obtained by multiplying by D. We also obtain that minus CBU equals C, minus CBU equals V, just by multiplying by C and by V, which means that C equals B, which means that A equals D. What else do we have? Okay, so as I mentioned, we have AC minus DB times U equals 1. But using these equations over here, we have that A squared minus D squared times U equals 1. However, this means that A minus D U equals 1. Sorry, beg your pardon.
A equal to D?
No, A equals to...
No. It would be a contradiction. Because A is equal to D, so A squared is equal to D squared.
And 0 is typically not invertible.
Oh, yeah. Sorry, beg your pardon. Sorry. No, this is... sorry, because I miss... Now it's correct. Sorry. I didn't copy correctly this over here. I changed it.
Yeah.
Now it's all correct. This is B squared. This is B. Okay. So good. If we still use this equation, we have again that AU equals A and minus BU.
Sorry, just a stupid question. And what happened to A plus B? I don't see how you got rid of it.
Because A equals D and C equals B.
Yeah,
because...
but
so what?
A squared is equal to A and D squared is equal to D.
Also, yeah.
B.
But okay,
about?
A squared is A. Okay, I forget it. Yes. Okay. Yeah. That's what I forgot.
Sorry. So if you multiply, again, this equation times A and this equation times B, you obtain these two over here, which means that A plus V times U, sorry, A plus V equals A times U minus V times U, which is actually A minus V times U, which is 1. So we can say that V is 1 minus A. So what we have is that automorphisms for A1 are isomorphic to matrices of the form I1 minus I1 minus I such that A squared equals A. Good.
But A is invertible or not?
Oh, I don't thought.
It doesn't have to. You
No.
only have. You only need this.
Mm-hmm.
Good. And also observe that 1 times 1 equals 0. So they form an orthogonal set of idempotents.
Yes.
So let's obtain now the Hopf algebra of this. So in order to obtain the Hopf algebra, at least in the way that they use in the Waterhouse book, they keep in mind that the elements of this group can be seen as morphisms of the representing algebra to the algebra R. So by using that, by using that, you obtain that H. First of all, how many variables do you need to obtain all the information in this group? You only need one, and it has to verify this equation. So H can be seen as that's all, which is isomorphic to K2. Why is that? Well, you just use the Chinese theorem, the remain theorem, and this is isomorphic to.
So this is an isomorphism as an algebra.
As algebras, yeah.
Saying nothing yet about the group.
The Hopf algebra, yeah. But I will say it later. This, no, not a square, sorry. Now, which is K2. Okay. So in this case, the product is given by the product here. So if you have the product A of 1 minus square.
So it's a cyclic group of order 2.
Yeah, there is. V1 minus V, sorry. 1 minus V. This is given by A times V plus 1 minus A, 1 minus V, A times 1 minus V plus V 1 minus A. The same goes here. And the same goes there. Nice. And the inverse is itself. If you multiply, you obtain the identity, which is the identity element in the group. So just using this, you can obtain the product, the coproduct, and using this, you can obtain the inverse. How do you do so? So if you have delta that goes from kx x squared minus x, it goes to sorry. Let's do it. X minus x which is given. If I use the var to define, to use as the equivalent classes, the generator x goes to x times x plus y minus x times 1 minus x. The co-inverse is given by the identity and the augmentation is given by 0.1. Okay, and this is the whole algebra representing the affine group scheme related with the automorphisms of A1. And observe that this whole algebra, if I'm not wrong, is the algebra K2 with the given by the span, or you can see it as the span of E0 if E1 with the coproduct from K2 where E0 equals 1, 0 if I'm not wrong, and E1 equals 0, 1 from K2 to K2. E1 E0 goes to E0 times E0 plus. Maybe you are more familiar with this. E0, E1, E1 times E0 plus E1. No, this is not right. E1, E0 times E1. And S given from K2 to K2.
No.
Going to A0 to E0, E1 to E1. And the augmentation going to from E0 to 1 and E1 to 0 if I'm not wrong. And this is the Hopf algebra representing the affine group scheme C2, the constant group affine group scheme of the cyclic group of order 2. Here you can see that this is the product. You get E0 times E0 is 0, and E1 1 times 1 is the order 0. I should have used maybe here gamma or something like that to make it different from 1. Okay. And also observe that actually, in this case, the algebra, well, you can see it as K2 or as Kx times x. As algebras, in this case, and we will see something related later, is isomorphic to the evolution algebra. In this case, the evolution algebra is associative, which is not something that happens all the time, but it happens in this case. You can see it here. This is just K2 with the component-wise product. Okay.
And could you give me an example of two-dimensional evolution algebra which is not associative, or will you have it later on?
For example, A2, the one that which is let me check. For example, A2 is, I always forget. For example, A2 alpha, which is A1 square equals A2, and A2 squares equals alpha E1 with alpha different from 0. For example, if you multiply E1, E2, you obtain 0. However, if you multiply E1, E2, E2, you obtain E1 times alpha E1, which is alpha E1 squared, which is alpha E2, which is different from 0.
Alpha E1, you mean?
E1.
No, alpha E2.
Alpha 1
yes, E1 squared is E2. Okay.
Yeah.
Okay.
Good. So, sorry. Let's come back to the slides.
Thank you. This is what I wanted to see. Thank you.
Let's go back to the slides. We've done like this type of computations. We did with all the other families. This one is like the shortest one. That's why I decided to show that to you. But the other ones are quite more trickier. They are trickier, yeah. Okay, let's see if I can share. Okay, good. So I was here. Okay, good. And after computing all of the different cases, we obtain this table over here. This is the perfect case. This is the affine group scheme that we associate to the evolution algebra, and this is the Hopf algebra that represents this affine group scheme. This is the one that I've already done. I've also mentioned this one. This is the trivial affine group scheme with representing Hopf algebra, the ground field. In A2, a very interesting example is A2 alpha, which is isomorphic to the product of mu3 times the affine group scheme C2. And from the...
I see semi-direct product.
Yeah.
Not a product. It's a semi-direct product.
Yeah, it's a semi-direct product. Yeah.
Okay.
And for the non-perfect case, we obtain all these families. Here there are more variety of them. We have the GA, GM. These are the semi-direct product of affine group schemes. And for the characteristic 2 version of the A8 alpha, we obtain this. I haven't add the Hopf algebra structure because that would take me like a very big table, but you can check it on the paper if you want. Okay, but well, once you have the affine group scheme, the Hopf algebra is completely determined. Okay, so we have seen evolution algebras. We have seen how to associate an affine group scheme to an evolution algebra. So the next step, and as I want to see, is what a representation of our evolution algebra is. In this case, a universal associative commutative unital representation, and it's given by the following. So they were introduced by Alexander Kornev and Ivan Shestakov on a paper called Associative Representation of Non-Associative Algebras. They do this in general, and for example, trying to replicate what happens in Lie algebras. And for example, with this, they can find a way to model octonions as part of an associative algebra. So how do we do that in case of dimension 2 at least? So we just consider a polynomial algebra of 4 variables, x, y, x star, y star, and an involution given by x goes to x star and y goes to y star. And we select a collection of a scalar of a field K and a product or a polynomial given by this combination over here. This using the involution is what the twist of the product you obtain is what you, yeah. So if you use another morphism or another automorphism, you would obtain another type of associative representation, but we have studied this family of representations, okay? For an evolution algebra, or two-dimensional evolutional algebra with basis this one, we consider in general this product over here. So what we want to do is to build an star ideal I such that you can obtain an homomorphism of evolution algebras that goes from A to UP, with UP being the quotient of this algebra over here, with E the ideal that we have built, the star ideal, and it's a morphism of algebras in the sense that the product of two elements is the twisted product of UP using the product here, P, instead of the associative one. Okay, so what is the ideal that we have to build? So it's basically the ideal given by the product of the generators of the algebra itself, the product x minus the product that we want to obtain in the evolution algebra, and pxy and pyx. So we obtain that these two elements are orthogonal, and also it's also this ideal is also generated by the conjugates. So in this way, the morphism rho that goes from A to UP, given by just E1 goes to bar to X var and Y, and E2 goes to Y var. We call that morphism the associative commutative unital representation of A, and the algebra UP is the faithful, well, in case that this representation is faithful, universal unital P algebra. Okay, with P, the product that we selected before. Good. And it is universal in the sense that if there is another associative commutative unital representation with the same P, an involution, and with an involution, then we have another morphism from UP to V of unital algebras with involution, such that you have this over here, this product. Okay. But that's the unital case. We can consider also the non-unital case. Instead of using the polynomials, you can use the free associative commutative algebra given by this variable and repeat the same construction over here. Instead of rho, I just call it R in a similar way. And TP is what we call the tight universal P algebra, okay? These are not unital versus the other ones they were, okay? And this one is related with the UP, as you can see. There's just no unit because UP is the unitation of this algebra. Okay, let's see an example. Again, going back to A1, which is an evolution algebra, which is also associative. So I think that gives you a clue of what's going to happen here. So again, A1 is the evolution algebra given by A1 squared equals E1 and E2 squared equals E2. So we just have to consider for a faithful representation the algebra of polynomials with two variables. And in this case, as you might already think, the involution that we will consider is the identity. And the product, what will be? The one given by the product in the associative algebra. The product of two elements is the product of two elements. So the ideal is generated by these polynomials here, and UP is this quotient. Again, if you consider the representation, so we obtain this rho given by these two elements, the image of these two elements, and it is faithful since this set of elements is linearly independent. Actually, this is an isomorphism. Well, it's not an isomorphism, so sorry. This is an isomorphism because you can consider the tight representation of this one using this quotient, not using the unit, which still remains faithful and is the associative commutative representation. And what we have, since this algebra is associative, is that the tight representation is isomorphic to A1, which, as we already mentioned before, is isomorphic to its representing Hopf algebra, which happens in this case because A1 is associative and also because A1 is perfect, as we will see. So how are we going to study faithful universal associative representation? What will be the strategy? At least the one that we follow in the paper. We just consider one of the algebras in the family of two-dimensional evolution algebras. We take a polynomial in this way with variables lambda 0, lambda 1, lambda 2, lambda 3. And we have two options. We find a collection of lambda such that var x and var y are linearly independent, or we explore all the possible values and see that this set is always linearly dependent. So there's no faithful associative representation in the way that we have built with using involution and etc., etc. Maybe with another construction, with another twist, with another type of automorphism, you can find a faithful universal associative representation, but not the ones that we have tried, at least. To do so, we use several computation softwares. We use just our bare hands, but also we use a couple of results. Well, one and a corollary of one of it, which is this lemma, which says that if we have a perfect evolution algebra and if we have a faithful representation, faithful associative representation of this algebra, such that it verifies that ax squared is related to its conjugate and y squared is related to its conjugate, or which is equivalent to these two polynomials being in the ideal, then A is isomorphic to one of these three algebras, which are the ones that are associative in the family of two-dimensional evolutional algebras. In relation to this result, we can also have that if we have a faithful associative representation in this way, with x being related with x star and y being related with y star, then again, A is isomorphic to one of these three algebras, that is, A is associative. Okay? So after all the computations, the paper is quite long because of that. Even we tried to make it smaller, but we also, in order to do so, we have to, there are annex and some appendixes that we have to add in a web page, but there are lots of computations. So after that, we find all the universal representations and see if there is a faithful one or there is not any faithful one. And we see that for A1, A2 alpha, A5 alpha, we have faithful representations. However, this is not the case for A3 alpha, A4 alpha, A5 alpha beta with alpha different from beta. This is for the perfect case. And for the non-perfect case, we have way more example of faithful representations with different polynomials, given by this one, these values over here of product, these twists. However, for the characteristic 2 case of A8 alpha, there is not universal representation. So how all this information that I gave you relates, these automorphisms, these Hopf algebras, these representations? Well, we can summarize all of it in this theorem. So if we have a two-dimensional evolution algebra over a field K, we have that the automorphism is equal to identity if and only if there is no faithful P algebras for A, if there is no faithful associative representation. And if we consider H the representative of algebra, then there is a faithful associative and commutative representation for A, if and only if one of the following hold. The characteristic is different from 0 and H is not isomorphic to K, or the characteristic of K is equal to 2 and H is not isomorphic to this algebra or to this one. And if the algebra A is perfect and has a faithful type P algebra, then this algebra is isomorphic as algebras to the Hopf algebra itself that represents. And we can see this in this table over here, where we can check that when the cases that we have faithful, we have tie representation, we can check that in these cases is isomorphic to the Hopf algebra that represents this affine group scheme, and observe that we don't have a faithful associative representation in the case that we have that the scheme of automorphisms is a trivial one. This is for the perfect case. For the non-perfect case, mention that we haven't done yet the computation of the type representation algebra and see if it's isomorphic to the Hopf algebra or not, because if not, the paper will take too long and we won't be able to, we wouldn't have been able to publish it, I think. Well, it's a further work for a future. So in this case, again, you see that for the faithful case, you have that the algebras, the automorphism and the Hopf algebras are not isomorphic to the trivial ones. However, for the characteristic 2, we don't have a faithful representation because it's isomorphic to the trivial one. Or its Hopf algebra it's isomorphic to this one over here. Yeah, that was everything that I wanted to say. I don't know if I think I have 10 more minutes. So as I mentioned, this is part of this paper over here, which is a second part of this paper here. And that's all that I wanted to say. Thank you so much for the invitation. And if there's any questions or something that you would like to ask.
Okay, muchas gracias.
De nada.
Okay, so if there are no questions, you would have to improvise for 8 more minutes, but I hope there are some questions. Tomek, why don't you begin?
Okay, so I have a question about your definition of this automorphism. If you have, for instance, an associative algebra or commutative associative algebra with a universal coaction of a Hopf algebra, you have an additional condition that this commultiplication, this coaction is a commutative or associative algebra map, which is not required here. Your automorphisms preserve some presentation. They are compatible with some presentation. They do not preserve any kind of algebraic structure in the sense of variety of algebras. So from the beginning, my question would be, why do you call it automorphism group at all, or automorphism Hopf algebra at all?
No, I don't call it automorphism of Hopf algebras.
No, I'm talking about
the evolution algebra.
Yes, but why do you call this Hopf algebra an object of symmetries, of automorphisms of this object, whose algebraic structure is not specified? Because your definition was in terms of binary product, some distinguished set of generators being a basis, by the way, and then your automorphism, your coaction, must satisfy some shape of this presentation, which is not an algebraic structure. So this is strange from algebraic point of view, because usually by automorphism we mean some action preserving some structure, algebraic structure. So in this definition of automorphism, what is missing, in my opinion, is a proper definition of a structure which is preserved by this automorphism.
Well, you preserve the structure of as a module, which I guess it's a structure that we agree that is a module, and also it preserves the binary products. Once it preserves the products in the basis, it preserves the whole structure of the algebra by linearity.
So the structure you are preserving is simply this binary product. But
yeah, and the structure of module.
Yes, but my problem is that if this binary structure doesn't satisfy any kind of identity, it's like magma, then you are talking about automorphisms of some strange quotients of magmas.
Okay.
For instance, what is missing in the definition of automorphism is that, for instance, let's assume that we are a case of a commutative ring. Then we can speak about the universal coaction of a commutative Hopf algebra. But then you have a requirement that this coaction is a commutative algebra map.
Yes.
Okay. For instance, if you have associative algebra, when you are considering a universal Hopf algebra coaction, you are assuming that this coaction is an algebra map, at least.
Yes.
It's a default shape of forming an object of symmetries of some algebraic structure of some sort. Now you have a magma, and you are looking for an universal object of symmetries, which is a commutative algebra. And the structure of this commutative algebra and the magma are not related at all. So this philosophy deviates from the standard philosophy of considering symmetries of algebraic objects.
Okay.
I have nothing against, but
no, it's okay. This is
but then
that
people could ask questions like, for instance, why your object of symmetries must be a commutative algebra? Why it's not an arbitrary Hopf algebra, for instance? Why it is not an co-group object in the category of associative algebras? Why it is not a co-group object in the category of magmas?
Yeah.
So all these things would provide some versions of symmetries of your object, and you are focusing on the action of a classical group scheme on your algebraic object. So this is my objection. Okay, but it's only terminological. Logically, everything's okay.
Okay.
I couldn't spot any logical mistake in this, but it makes this approach a very strange part of mathematics.
It is. This kind of thing. It's something that another in another congress someone asked something similar. It's a mathematician who has worked most of his life in Jordan algebras, and he has an objection similar to that one. And what he disagreed was that maybe the definition of evolution algebra is not complete because of the same fact as I mentioned before of like there's when you have a sub-algebra, it's not necessary an algebra and another evolution algebra. So I think like we were discussing this and we think, I don't know, this is not my topic at all. What I do is path algebras and Steinberg algebras and all very different stuff. Like I work on this, but not on my thesis. This was something that because I was studying affine group schemes and my supervisor wanted me to participate in here. So we were discussing that maybe like to make a complete definition that makes sense with what you're objecting is to add the hypothesis of being perfect or being regular because, for example, in this paper that I mentioned, they prove that when the evolution algebra is regular, then subalgebras are also evolution algebras. So maybe with that hypothesis, it all made more sense, at least for answering your objections. But I have to say that I still don't really understand, but because I don't know anything about coaction of algebras and things like that. So
okay, if I could suggest something, if you speak about a distinguished basis of your algebra, so what you are speaking about, in fact, is an additional structure of a coalgebra on this algebra.
Okay.
Okay, because if you realize your module or your vector space as a span of some set, then it automatically becomes a coalgebra.
Okay.
Okay, and then you could speak about your algebraic object as half magma and half coalgebra.
Okay.
Okay, but then if you are speaking about the symmetry object of this symmetry object, if it was a symmetry object of this two-sided algebraic and coalgebraic structure, it should be compatible also with this commultiplication. When this commultiplication comes from the diagonal map on the level of this basis. It's like doubling an element of a basis.
Okay.
And then I would check if these universal Hopf algebras, if they preserve this additional structure. Okay.
That's very interesting to do. Okay. Thank you.
But I agree, it's a very good idea to regard this definition of evolution algebra as provisorial, and continuing studying this to work out well-behaving structure, algebraic structure. Maybe not algebraic, but partly algebraic, partly coalgebraic, something like this. Because defining something by choosing a basis and defining something in terms of this basis, it's not a good habit in algebra.
It's not very good. But for example, when the algebra is perfect or it's regular, it can be proven that all the natural bases, or the orthogonal bases, as you want to call them, they are all the same up to reordination and scalar multiplication. And the graphs are all isomorphic. And so I think being perfect, it's a very good way to solve all this problem.
Yeah, so probably this notion of evolution algebra is deeper than this provisorial definition suggests.
Well, like actually the definition, when they just gave this, like an algebra that satisfy that, and even like the papers by Tian, or there is like a book by Tian. The thing is that it has lots of mistakes. So we have been, my colleagues and I, also Yolanda, which is she's the expert there, we have been making improvement, because this is a very new topic. Well, not very new, but it's quite new topic, and it's not something that most of the people have studied yet. And since this weird thing of everything just being zero or different from zero, like this tensor being diagonal, makes the definition very easy, but very weird and strange things happen. So yeah, I completely understand why you object with that.
Okay, may I ask the last question?
Sure.
Could you explain the difference between this Mendelian and non-Mendelian genetics.
Oh, basically,
I know for it. So please let me explain why I'm asking this question, because I'm familiar with the approach of Hardy to this Mendelian genetics.
Mm-hmm.
You know, this Hardy, who said that his inventions will be not used in practice. He was very proud of this. But his discovery in
using
Mendelian
banking,
genetics
yeah,
was,
I know.
Yeah. So are you familiar with these Mendelian laws of Hardy?
No, I have no idea at all.
So okay. So what about this non-Mendelian genetics? What is the idea?
Basically asexual reproduction.
Asexual reproduction.
Yeah, you like one individual reproduce by itself. It's, for example, like, I don't know, bacteria or like elements that replicate, and so the DNA that doesn't get mixed. So the idea of evolution algebras and in the start.
So you have only mutations.
Exactly.
You don't have recombination.
Exactly, but you have mutations.
Okay,
that's why. So that's why here the way this models this type of reproduction, because let me check. Do you still see my?
Yes.
Yes.
So what you get here is basically these are all the genes that are more like you are interested in an individual, and since it's reproduce so it doesn't reproduce with another individual, so you don't get like any recombination or something like that. That's why the product is 0. It only reproduces with itself. However, since there are mutations, one gene can change into a combination of them with a probability.
So this must be related to Markov chains.
Exactly, they are very related with Markov chains, and also there are a type of evolution algebra that comes from Markov chains. They are very, very related. But I still, again, I just know a little bit of Markov chains. I just know a little bit of why they're related. But my colleague is very, because she's also she also studied the statistics, so I think she will answer way better than myself. But yeah, that's what this representation. But what we have done is forgetting about the model, forgetting about what it does. We just focus on studying the algebra by itself.
Yeah. Okay, thank you.
And here, you typically in algebra, you only have commutants, but you also have mutants.
Yeah.
Anybody else? Adam?
No, I'm happy. Thank you.
Anybody else?
Yes, may I have a small question?
Yeah.
I wonder if the matrix algebra, for example, of dimension 2, a 2x2 matrix, is there a natural base for the matrix algebra? I mean that for a given associative algebra, what kind of abstraction exists to consider that algebra as an evolution algebra? Let's consider the most simplest case, for example, M2C, the matrix algebra of 2x2 matrix. Is there a natural base for this algebra?
Natural in this specific sense, yes.
Yes, in this specific sense. Because the standard base of the matrix algebra doesn't satisfy this property of EI, EJ equal to 0. But during your talk, I was wondering and thinking to existence of another base. So is it a good idea to?
I certainly, I don't know if matrices are evolution algebras, like an algebra of matrices. I don't know.
But don't you have a contradiction in terms of dimensions?
Sorry, beg your pardon?
Don't you have a contradiction in terms of dimensions? No?
Why? In terms of dimensions?
Well, you have n squared is the dimension of your matrix algebra. So could you cook up a basis? Yeah, okay, sorry, I take it back. Yes, in principle you could. It's not obvious. Yes.
Yeah, I don't know if you can find a basis that is like an evolution algebra, a natural basis, or you can prove that there's no natural basis at least by now. What would happen? There is. It also, I know
seems computable. I mean, you could just run a computation actually, right?
Yeah, that's the thing that you should check. But that's not very, for me, it's not very smart, like not very elegant.
Yeah, yeah. But maybe the question can be algebra. Maybe the question can be rephrased: is there any obvious criterion which allows you to tell that a given algebra, no way, it cannot be an evolution algebra? So, for instance, when we look at graph sister algebras, they have many, many prominent features, and we can immediately, just by looking at extremely basic properties of sister algebras, say that they cannot be graph sister algebra. So maybe it's in the same spirit.
No, at least by now, at least I don't know if there is any criterion. I don't know, maybe because what we are doing, for example, is studying some structures like circle, radical, things like that. Maybe comparing that, like, for example, if we have enough tools, like we have enough knowledge of evolution algebras, maybe by checking, like, okay, we have this algebra, let's see its circle. Okay, if this is an evolution algebra, the circle should be something like this.
Precisely.
But by now, there's not, at least I don't know anything. And the thing is, evolution algebra, there are very weird things happen to them, like, which are not very obvious. And things like, I don't know, there is not, usually they're not unital, or they're not associative. Again, a subalgebra of an evolution algebra doesn't have to be an evolution algebra. So my question, but my answer right now is we don't have an answer yet. But again, maybe following Thomas' suggestion, by adding perfect to the definition, we will obtain more results in the future.
But it was a very good question, Ali. Yes, thank you.
Thank you. Thank you. And thank you very much for your very interesting talk.
Thank you. Sorry if I couldn't fully answer your question.
No,
so maybe to wind it up, let me ask two very naive, simple-minded questions related to your discussion with Tomek.
Okay.
One is, typically mathematics is created or discovered in order to solve problems. So I would like to understand what kind of problems, except for, as Tomek put it, in order to give a deeper, more substantial concept.
Piotr, you're mute. Oh, Piotr is frozen. Piotr is frozen.
Okay, so I was like, something happened.
Piotr, I don't know. Can you hear us?
Yes.
Yeah, I can hear you quite
frozen
nice.
For a while. We lost your comment or question. So now he disappeared completely.
Yes, I think.
Maybe this is the end.
No, my internet collapsed. Can you hear me now?
Yes.
Okay,
that's
sorry.
Good.
Yeah, I'm still very happy that it collapsed only at the end, because a week ago it collapsed 4 times during the talk. Okay, so yeah, but did you hear my question, or should I repeat it?
Only the first part. If you could repeat it.
So I was saying that typically mathematics is discovered or created or invented in order to solve problems, and I'm wondering what kind of problems are you solving with this formalism? Maybe in addition to what Tomek already mentioned, that this study that you are looking at digs into the very conceptual meaning of what these evolution algebras are supposed to be. But do you solve any concrete problems by having all these tight representations and all these nice commutative Hopf algebras? For instance, studying quantum symmetries of graphs allows to determine that two graphs are non-isomorphic, which is completely undoable without the symmetries. So that's the type of question I'm asking.
At least right now that I know, there is not any problem like that is related to evolution algebras. Not that I know. Again,
okay.
I have like
okay.
I'm just how would I say handwork, like I'm just a worker here, like I just I know of evolution algebras as the same as you do. I just know the definition and I just work with them because I'm not an expert in this topic. Like I think I might know more of affine group schemes rather than evolution algebra, and even I don't know anything about affine group schemes.
Okay,
so,
and my related question is about graphs. So for starters, as I already mentioned before, I'm kind of puzzled why on earth you talk about directed graphs, not labeled directed graphs. I mean, your very definition begs for a labeled directed graph.
Yeah, well, I have to say that I don't really know why we didn't like this introduction of the graphs was done by Alberto El Duque and Alicia Labra. I don't know if you have heard of Alberto El Duque. And I don't really know why, like, they obviously use a labeling. We obviously do that. We try to work in a category of label graphs. We try to replicate that, keeping in mind that we have weights, that we have weighted graphs. But in general, I feel like they just wanting to see a combinatorial way to see the evolution algebra with just a simple glance. Because if not, having the graph with the weights and having the structural matrix is the same. You get all you get all the information of it, but you still can obtain some properties of the evolution algebra just by looking at the graph without the weights, just by their combinatorial structure or topological structure. So
okay,
my answer would be, I don't really know. Like I would consider it as labeled graphs instead of just directed graphs. But we usually try to use as much information as we can. We have another paper where we just commit to non-label, and we see that there are some properties that can be checked with just by looking at the graph. But we also know, and we have several examples of certain properties like semi-Artinian, semi-primitive, semi-prime or prime, things like that, that by checking just the graph, it's not enough. However, again, following Thomas' objection, with the perfect case, there are many properties that can be just obtained with the directed graph, without the weights and without the labeling. Maybe just using the graph makes sense for perfect algebras. Well, it actually does, because for the perfect case, all the graphs are isomorphic, depending on by changing bases. So maybe that's why
it's good.
Maybe most of the people just restrict themselves to the perfect case. Because it's
because you see, for graph sister algebras, even for Leavitt path algebras, the amount of information that you can read out of a graph is just enormous. For starters, you have K-theory on the plate, which is something very, very non-trivial. If I give you an algebra and you are supposed to give me K-theory, that's quite a big task generically. But for graph sister algebras, we have an algorithm. AI can compute K-theory from the graph. So that's very, very important. There are also many other properties that you can deduce just from the structure of a graph. even for path algebras, you can read out the Jacobson radical from the graph. So could you please remind me what are the properties of your evolution algebras that you can read out of a graph?
That you can read from
What
the
you
graph?
can read out of a graph, conclude just from the combinatorics of a graph. Because
right
I
now,
was hoping for much more interaction between combinatorics of graphs and properties of algebras.
Well, by memory, I know that, for example, you can check, for example, if you have a sink or a source, you already know that it's not perfect.
Okay, that's good. Okay.
You can also check. I don't completely remember, but for example, there are other properties that are combinatorial properties. For example, if it is associative, you can check it at least partially looking at the graph. I know that being prime in the perfect case, you only need for the graph to be downward directed. That means that the evolution algebra is prime.
Perfect.
For semi-prime, I think you cannot obtain that. Well, I don't really recall that right now, but you can check in the archive. We have a paper called, let me see, what was the name? Where we check several properties. Also, for example, you can compute the centroid of the algebra by checking paths of length 2.
Perfect.
And also the associative nuclei, the associative core, the associative nuclei. I don't know the name in English. Well, there's another structure that tells you like kind of associativity that can also be checked with the graph, but there's still missing information. The paper was called the paper is called Centroid and Algebraic Properties of Evolution Algebras Through Graphs, which is done by the same people as this paper that I mentioned before. And there you can check several combinatorial properties that you can check using the graph. Like the several non-degeneracy, von Neumann regularity, etc., etc. But yeah, there are also other many properties that you cannot obtain by just looking at the graph. But by looking at the label graph, obviously, because you have all the information there.
Well, you gave me a perfect and very satisfactory answer. I really am very, very happy with your answer. I only regret that you didn't unravel it in detail of what you just told me, because I would be very happy to see the details of what you just mentioned in words. For me, that part is far more interesting than this whole algebras. But I'm very happy that there is such a deep and important answer to my question, because now I'm happy with the usage of graph. It's completely justified after what you.
I also more interested in the use of the graph, because that's what I do. I've been studying path algebras for my whole thesis, so I really like to try to obtain algebraic properties of the evolution algebras just by the graph. And that's something that we have previously done, and my colleague has done, and my supervisor also, Daniel, has work of that. So yeah.
Muy bien, muy bien. So muchas gracias, our speaker again. Thank you so much.
You're welcome.
I stop recording.
Nice.